Good evening everyone, good evening. I welcome you all again to VJEE Enthuse. I hope you guys are doing great, having a good time. Well people, you can let me know in the chat box if I'm audible and visible to everyone. Hello JEE Enthuse fan club, hello Akshaya, hello Rajat, hello Deborah, hi Shrikant, hi Ashwarya, hi Devansh, hello Shruti, hi Vimulri. Welcome everyone, welcome. Hello Samita, hello Yashwa. Welcome people, welcome back to VJEE Enthuse. Yeah? Just let me know, give me some green signal from the chat box so that I'll get to know whether I'm audible and visible to you or not. Yeah? Just give me some green signal from the chat box. Yeah? Perfect guys, perfect. All right, so as you all must be knowing, tonight, it's going to be a session, lecture number 3 from the chapter Chemical Kinetics, yeah? In the last session, if you remember, we discussed something called as law of mass section, we discussed rate law, molecularity, order, everything was discussed in detail, yeah? Okay, yes, JEE Enthuse fan club, you can definitely expect some kind of motivational videos from me. I know I have never done that before, yeah? I'll try to do that for you, no issues. Perfect. So the ones who are new to the channel, let me introduce myself. My name is Wassim Sir and I'm your chemistry master teacher right here on this VJEE Enthuse channel. Yeah. Okay. Yashwa, I take morning classes on NEET Elite channel. Okay. The ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel and do not forget to hit the bell icon so that you get the notification of every single session which I'll be taking live on this channel. Yeah. Okay. So people, you can let me know in the chat box if you guys are super duper excited about the session. Siddharth, I have no idea like why Shimon sir didn't take the class. Maybe he's not well. I never knew he didn't take the class. Okay, I'll call him like after the session. Yeah. I did not know that he couldn't attend the session. Chalo, let me know in the chat box if you guys are super duper excited about the session. Let me know in the chat box. Yes, definitely Shimon sir won't be well. That's why he has not taken the session. Otherwise, he doesn't miss a single chance of taking the session. Yeah? he's very much punctual about the classes. Very much punctual. Perfect, guys. Okay. So what all things we are going to cover, first of all, in the tonight's session, we'll be starting with something called as experimental determination of the order of the reaction. We'll be discussing about the zero-order reaction. We'll try to derive the integrated rate equation for the zero-order reactions. We'll be talking about the half-life of the zero-order reaction, and at the same time, we'll be talking about what? We'll be talking about the completion time of a zero-order reaction. All these things I'll discuss in the tonight's session. Okay? So this session, I'm going to start with the question, then we'll be moving on to something called as experimental determination of order, right? But first, I'll be starting this session from the very simple question over here. It looks complicated, but it's not complicated at all. Yeah? See guys, what the question says. Understand properly what I'm going to say. All right. Okay, so as per the question, we are given with a reaction H2 plus Br2 gives 2 times HBr. Yeah? I'm given with the rate expression for this reaction over here. And as per the rate expression, rate of the reaction is equal to K1 multiplied by concentration of H2 multiplied by concentration of Br2 raised power 1 by 2 divided by concentration of Br2 plus K2 multiplied by concentration of HBr. This is the rate expression which I am given with for this given balanced chemical equation. Okay. What am I supposed to calculate as per the equation? Calculate the order of the reaction. We are supposed to calculate order of the reaction. Number 1, if the concentration of Br2 is very high. Number 2, if the concentration of Br2 is very less. Okay, so these are basically two questions over here. See guys, how to approach to these sort of questions. See, whenever you'll be given with the rate expression in this complicated form, what you'll be doing over here is, you'll try to convert it into the simplest form. You'll try to convert it into the simplest form. And how we are going to do that? There are some conditions given to me. By using these conditions, I'll try to convert this complicated rate expression into the simplest form. Yeah? And how to do it? Understand. See guys, as per the first part of the question, if the concentration of Br2 is kept very high. Well, as per the first part of the question, if the concentration of Br2 is kept very high. Well people, if the concentration of Br2 is kept very high, at that time, this term in the denominator can be neglected in comparison to concentration of Br2. Well, as per the question itself, I'm keeping the concentration of Br2 very high. And if I'm keeping the concentration of Br2 very high, instead of concentration of Br2 plus K2 multiplied by concentration of HBr, I'll be only writing what? I'll be only writing concentration of Br2. Correct? Okay, the job is almost done. Now people, as per my rate expression is concerned, rate of the reaction is equal. I'll be simply writing K1 multiplied by concentration of H2 raised power 1 multiplied by concentration of Br2 raised power 1 by 2. Yeah? Whole divided by. Instead of this whole term, I'll be only writing what? I'll be writing concentration of Br2. Yes. Now. After this, what am I going to do? I'll simply say rate of the reaction is equal to K1 multiplied by concentration of H2, right? Over here, we have got concentration of Br2 raised power 1 by 2 divided by concentration of Br2 raised power 1. So it is going to come as like this. I'll be writing concentration of Br2 raised power minus 1 divided by 2 in short, yeah? Because when I'll take this Br2 in the numerator, it becomes Br2 raised power minus 1, right? Then we have got Br2 raised power 1 by 2 multiplied by Br2 raised power minus 1. That comes out to be Br2 raised power minus 1 by 2, right? Now people, this is the simplified rate expression which I have made over here, yeah? Yes. Now if you remember how we used to calculate the order of the reaction. Simple. Order of the reaction is the sum of powers of these concentration terms which are involved in the rate law, right? Whatever is going to be your rate expression, right? In the rate expression, whatever is going to be the powers of these concentration terms, you need to simply add the powers of these concentration terms. That gives you the overall order of the reaction. Yes? So you can say the power right here is 1, the power right here is minus 1 by 2. So overall order of the reaction is going to be equal to 1 plus minus 1 by 2, and the value will come out to be 1 by 2. So order of the reaction is going to be simply 1 by 2. The first part of the question is done. We have calculated the overall order of the reaction when the concentration of Br2 is kept very, very high. Yeah? As simple as that. Okay? Right? The first part of the question is done. Moving on to the second part of the question. The second part of the question is again very, very simple. Well, as per the second part of the question, if the concentration of Br2 is kept very less, yes? So people, as per the second part of the question, the concentration of Br2 is kept very, very less. And when the concentration of Br2 is kept very less, at that time, concentration of Br2 plus K2 multiplied by concentration of HBr. I'm talking about this denominator. If Br2 is kept very less, at that time, this plus this will be equal to K2 multiplied by concentration of HBr, right? Okay, this is the second part of the question, right? Now we will understand. As per my rate expression is concerned, rate is equal to K1 multiplied by concentration of H2 raised power 1 multiplied by concentration of Br2 raised power 1 by 2 whole divided by. Instead of Br2 plus K2Br, K2HBr, I'll be only writing what? I'll be only writing K2 multiplied by concentration of HBr over here, right? This is something which I wrote, correct? Yes. Now we will see. Your K1 is constant, K2 is constant, division of two constants becomes one more constant. So I'll be writing rate of the reaction is equal to division of these two constants will become one more constant which I'm representing by K dash. It's simply going to be concentration of H2, yeah? Now over here, we have got concentration of Br2 raised power 1 by 2 and take this concentration of HBr in the numerator, it's going to be concentration of HBr raised power minus 1, yeah? Now this is my simplified rate expression, okay? So people, in this rate expression, you have got three concentration terms. Just look at the powers of these concentration terms. The power over here is 1, the power over here is 1 by 2, the power over here is minus 1. Just add them up, just add these powers up. What you'll be getting exactly? You'll be getting the order of the reaction as 1 by 2 again. So again, the overall order of the reaction comes out to be what? Again, the overall order of the reaction comes out to be 1 by 2. So in both the cases, the overall order of the reaction comes out to be 1 by 2. Yes? Right? Let me know in the chat box if it is clear to you. Yes? Ronak, it's not going to be 2 by 1, it's going to be 1 by 2. Let me know in the chat box fast if it is clear to everyone. Let me know fast in the chat box. Akshay, I think you are in the wrong channel, yeah? Just give me some thumbs ups in the chat box so that I can move on to the next topic, yeah? Perfect, guys. Wonderful. All right, so let's move on. And let's get to know how the order of the reaction is calculated experimentally, yeah? Okay, let's get to know how the order of the reaction is calculated experimentally, okay? People, directly you are given with a question, and by solving this question, you'll get the clear-cut idea of how the order of the reaction is calculated experimentally, okay? Now, how this question is to be solved, how the order of the reaction is calculated experimentally. First of all, I'm given with the reaction 2 times NO plus 2 times H2 gives N2 plus 2 times H2. Rate constant of the reaction is K, okay? In order to calculate the order of the reaction, what I'll be doing over here is, I'll be simply writing the rate law for this given reaction. And as per your rate law, you write the rate of the reaction is equal to rate constant multiplied by concentration of NO raised power X multiplied by concentration of H2 raised power Y. This is how we write the rate law, yeah? Because in the last session only, I told you, whenever you need to calculate the order of the reaction, at that time, you'll be first of all writing the rate law, right? Since I have written the rate law for the given reaction, okay? Now, what all things are we given with as per the question? We are given with 3 experiments. 3 experiments have been carried out. In the experiment number 1, the concentration of NO is kept this much, the concentration of H2 is kept this much, and at that time it was observed that the rate of reaction is this much, yeah? Similarly, in the second experiment, the concentration of NO is kept this much, the concentration of H2 is kept this much, and at that time the rate of the reaction was found out to be this much, and similarly the third experiment was carried out, right? Now what I'll be doing? Understand properly. See guys, first of all, this is the rate law which I have written for the given reaction, okay? Now I'll try to put all the data of the experiment number 1 into this rate law, okay? If I talk about the experiment number 1, what is the rate of the reaction as per experiment number 1? The rate of the reaction as per experiment number 1, it comes out to be 3 into 10 raised power minus 5. 3 into 10 raised power minus 5 is equal to K, I'm writing as such. What is the concentration of NO which is kept in the first experiment? It is 5 into 10 power minus 3. 5 multiplied by 10 raised power minus 3 raised power X multiplied by. What is the concentration of H2 kept in the first experiment? It is 2.5 into 10 raised power minus 3 raised power Y. This is what I'm calling as equation number 1. This is what I'll be calling as equation number 1, yeah? Okay. Now people, similarly, in the same rate law, I'm going to put the data of the experiment number 2. And as per experiment number 2 is concerned, the rate of the reaction is 9 into 10 raised power minus 5. The rate of the reaction is 9 into 10 raised power minus 5 will be equal to K is the rate constant. What is the concentration of NO in the second experiment? It is 15 multiplied by 10 raised power minus 3 raised power X multiplied by what is the concentration of H2 in the second experiment? It is 2.5. 2.5 into 10 raised power minus 3 raised power Y. Let's call this as equation number 2. Similarly, I'll be using the data of the experiment number 3 in this given rate law. And as per experiment number 3, what is the rate of the reaction? It is 36 into 10 raised power minus 5. It is 36 into 10 raised power minus 5. It is equal to K multiplied by concentration of NO in the third experiment. It is 15 into 10 raised power minus 3. 15 multiplied by 10 raised power minus 3 whole raised power X multiplied by concentration of H2 in the third experiment, that is 10 multiplied by 10 raised power minus 3 raised power y. Let's keep this as equation number third. Since I got 3 equations, as you can see over here, I got 3 equations. Now people, what I'll be doing over here, understand. I'll be dividing equation number second by equation number first. I'll be dividing the 2 equations, second by first, okay? So 9 divided by 3 comes out to be 3 is equal. This 10 raised power 5, 10 raised power 5 gets cancelled out. This k and k gets cancelled out. So 2.5, this whole term gets cancelled out. So you get 10 raised power minus 3, 10 raised power minus 3 cancelled out. 15 divided by 5 comes out to be 3 and the power over here is x, okay? So when is this equation possible? 3 raised power 1 is equal to 3 raised power x. This is only possible when the value of x will be 1. So I got the value of x, which is coming out to be 1. That means I got the order of the reaction with respect to NO. I got the order of the reaction with respect to NO, right? My first term I have calculated. The value of x is calculated. Now, it's time to calculate the value of y, okay? Now, how do I calculate the value of y, okay? Now, what I'll be doing, I'll be simply dividing the third equation by the second equation. When I'll divide third equation by the second equation, it becomes 36 divided by 9, which comes out to be 4 is equal. K and k gets cancelled out. This whole term gets cancelled out. 10 into 10 raised power minus 3 divided by 2.5 into 10 raised power minus 3, that becomes 4 raised power y. When is this equation possible? This equation is only possible when the value of y again comes out to be 1, right? So people, as you could see over here, I got the value of x, I got the value of y, yes? So the overall order of the reaction is going to be simply x plus y. X plus y, which is going to be 1 plus 1, which is 2. So 2 is the overall order of the reaction which I was supposed to calculate. I hope you got the procedure of how to calculate the order of the reaction from the experimental data. Can you let me know in the chat box if it's clear to everyone? Can you let me know in the chat box if it's clear to everyone? It's okay, Gaurav, it's okay. Welcome back. Let me know in the chat box if it's clear to everyone, yeah? Exactly, the overall order of the reaction comes out to be 2, yeah? Just give me some green signal from the chat box so that I'll get to know whether it's clear. Okay, perfect guys. So we got the order of the reaction, overall order of the reaction as 2, yeah? There is one question which is going to be your homework. You're going to give it a try. You're going to let me know the answer of this similar type of the question in the comment section, okay? Please do give it a try and let me know the answer of this question in the comment section afterwards, yeah? Okay, this is the similar type of question. You're going to follow the similar procedure which I've shown you right now, yeah? Perfect guys. So let's move on. And let's talk about something called as zero order reaction. Let's talk about something called as zero order reaction. What is this zero order reaction all about, yeah? What is this zero order reaction all about? So let's try to understand this zero order reaction over here. Let's try to understand this zero order reaction over here. See guys, as per the definition of the zero order reaction is concerned, that reaction in which the rate is independent of the concentration of reactants. If you'll be having any sort of reaction in which rate of the reaction becomes independent of the concentration of reactants, that is something which I call a zero order reaction. For example, have a look. Okay, say guys, let's assume I'm taking a reaction as A gives B. It is a complete balanced equation, for example, yeah? It's a balanced equation. It's a balanced chemical equation. Let's assume its rate constant is K. Let's assume order of this reaction is equal to 0. Okay, order of this reaction is 0. Any reaction which has got order equal to 0, that's what we call a zero order reaction, first of all, yeah? Now people, I'm writing time t is equal to 0. What does that mean? That means the reaction has not started yet. The reaction has not started yet. I'll be only having a reactant with me at time t is equal to 0. And let's assume the concentration of reactant at time t is equal to 0 is A0. If I ask you, what is the concentration of product at time t is equal to 0? It is going to be 0 because the reaction has not started yet. The product has not got formed yet, okay? Now, what is going to happen with the time? When the reaction will start, the reactant will start getting converted into the product. So with time, the concentration of reactant will keep on decreasing and the concentration of product will keep on increasing. Let's assume at any time t, the concentration of reactant left is 80. 80 is the concentration of reactant left at time t. Okay? And for example, Bt is the concentration of product that has got formed at time t. Okay? What is 80? 80 is the initial concentration of reactants when the reaction has not started. 80 is the concentration of reactant left at time t. I'm going to write it over here so that you can remember it from now onwards, because everywhere I'll be using this A naught and 80. You should be careful with its meaning. A naught is what we call as the concentration of reactant at time t is equal to 0. And what is this 80? 80 is the concentration of reactant left at time t. Concentration of reactant left at time t, correct? Now people understand properly what I'm going to say. Since it's a zero order reaction, okay, I'm assuming the reaction to be zero order. Can I write its rate law? Absolutely. As per its rate law, rate of the reaction is equal to K multiplied by concentration of reactant, that is only A, right? And the power of this concentration term is going to be 0 because order of the reaction is 0. Yeah? This is its rate law. This is its rate law. Rate of the reaction is equal to K multiplied by concentration of A raised power 0. Similarly, I can write the rate of the reaction from the stoichiometry as well, if you remember. Since I'm assuming the reaction to be a balanced chemical equation, so rate of the reaction is going to be minus times change in the concentration of A divided by dt, correct? Right? This is the differential form of rate. This is the rate of the reaction as per rate law. This equation is giving me the same thing. This equation is giving me the rate of the reaction. Even this equation is giving me the idea about the rate of the reaction. Okay? So people, if this equation is giving me the rate of the reaction, if this equation is also giving me the rate of the reaction, at that time I can simply equate the two. Yeah? And when I'll equate these two, I'll be getting something as minus times change in the concentration of A divided by dt is equal to K multiplied by concentration of A raised power 0. Correct? This is something which I got till now. Now we will understand what I'm going to do. I'm going to write, see, A raised power 0 is 1, we know it. So I'll be writing change in the concentration of A is equal to minus times K multiplied by dt. Since I'm going to derive the integrated rate expression for the zero order reaction, so I'll be basically integrating on both the sides. On this side, I'm integrating with respect to time, and time is changing from 0 to t, so it is 0 to t, correct? And on the left hand side, I'm integrating with respect to the concentration of A. On the left hand side, I'm integrating with respect to the concentration of A. And at time t is equal to 0, what was the concentration of A? That was A naught. And when the time was t, at that time, concentration of reactant A was AT. Correct? So I gave my limits as well. I gave the limits as well. When the time was 0, at the initial conditions, the concentration of reactant was A naught. At time t, the concentration of reactant is going to be AT. Now simple, just use the integration. As you all must be knowing, integral of dx is equal to x, correct? Similarly, integral of dA is going to be A. Now you are going to put the limits from A naught to AT, correct? It's going to be minus times K. Integral of dt is going to be simply t, right? So just put the upper limit, which is AT, put the lower limit, which is A naught, is equal to minus KT. So you get a final equation as AT is equal to A naught minus KT. This equation is something which I call as integrated rate equation for the zero order reactions. This is something which I call as integrated rate equation for the zero order reactions. Okay, this is something which I call as integrated rate equation for the zero order reactions. Point number 1. This is the equation which I'll be using in order to solve majority of the questions which are based on these zero order reactions. Correct? Okay. Now you will understand few more things. I'm sure you would have copied everything till now. Okay, I'm erasing this part completely. Right? So first of all, for a zero order reaction, rate law is expressed as R is equal to K multiplied by concentration of A raised power 0, correct? And at the same time, what about the differential form? What about the integrated rate expression for the zero order reaction? It's AT is equal to A naught minus KT, correct? Okay, Now people, I'll try to plot two curves over here related to the zero order reaction. Plot number one is going to be rate of reaction versus the concentration of reactant. Okay. Plot number two, it's going to be AT versus T, where AT is the concentration of reactant left at any time T, right? AT versus T. People, you can clearly make the curves over here. See, rate versus concentration of reactant. Rate versus concentration of reactant. We know zero order reaction is the one in which rate is independent of the concentration of reactant. So the curve is going to be a straight line. If you will change the concentration of reactant, rate of the reaction is not going to change at all. Yeah. This is going to be the curve which will be only valid for the zero order reactions, because only in case of zero order reactions, on changing the concentration of reactant, the rate of the reaction is not going to change at all. Yeah. Rate of the reaction will have a fixed value. Yes, I'm sure it's clear to everyone. Similarly, if I'll try to plot one more curve between AT versus T, just look at this equation. I'm plotting AT along y-axis, I'm plotting T along x-axis. Instead of this AT, I'll be writing y. Instead of this T, I'll be writing x. This is something which I'll be calling as m. This is minus sign, and this is something which I call as intercept. Y is equal to m minus mx plus c. Y is equal to minus mx plus c. The curve is going to be a straight line like this, okay? Right? And the slope of this curve is equal to minus k. Slope of this curve is equal to minus k. And what about the intercept? Intercept is the distance from the origin to the point from where the curve starts. That means this distance. This is what I call as intercept, which is denoted by c, and c value in this case is equal to a naught. This is again one more curve which is only valid for the zero order reactions. Remember this as well. Just let me know in the chat box if you're clear with this. Yeah. Let me know in the chat box if you're clear with these things. Fast. Fast, let me know fast. Perfecto. Just give me some green signal from the chat box so that I can move on. Yeah. Let me know fast in the chat box if it's clear to everyone. Perfect, guys. Gaurav will be doing that as well. Hello, Ishfaq, how are you? Amarnath, I'm not getting what? Big AC, sir? What is AC? Thank you, Arif, thank you. All right. Perfecto. All right, guys, let's move on. Now let's get going. Let's talk about something called as half-life of the zero order reaction. Okay, just give me a second. Let's get going. Let's talk about something called as half-life of the zero order reaction. Now the point is, what is this half-life of the reaction all about? How do we define it? It's a very simple thing. As per its definition is concerned, the time taken for the concentration of reactant to reduce to half of its initial value. The time taken for the concentration of reactant to reduce to half of its initial value, right? Okay, what it means exactly, have a look. Let's assume, okay, let me write it over here. Let's assume I have got a zero order reaction, A gives B. Okay, I'm directly starting with a zero order reaction. Its rate constant is K. Okay, let's assume at time t is equal to 0, the concentration of reactant is, for example, 4 molar. For example, at time t is equal to 0, the concentration of reactant is 4 molar. Now, when the reaction will start, what is going to happen to the concentration of A? Concentration of A will decrease with time. Can I say there will be a time when the concentration of reactant will be 2 molar, right? The time taken for the concentration of A to reduce from 4 molar to 2 molar is something which I call as T half-life, right? Okay, this time interval is what I call as half-life. The time taken for the concentration of reactant to reduce to half of its initial value is something which I call as half-life of the reaction. Okay, if I'll try to generalize it, Let me generalize it. Let's assume at time t is equal to 0, the concentration of reactant is A0, the concentration of product is going to be 0. Now what's going to happen with time? When the reaction will start, the concentration of reactant will decrease with time, and there will be a time which I call as half-life, at which the concentration of reactant left will be A0 by 2. And the concentration of reactant left is represented by AT, right? AT is the concentration of reactant left at half-life, correct? As simple as that. And this time interval from 0 to t, this time interval is something which I call as half-life of the reaction. The time taken for the concentration of reactant to reduce to half of its initial value is something which I call as half-life of the reaction. Okay? Now we will understand. See, if I consider this condition over here, well, as per my integrated rate equation is concerned, AT is equal to A0 minus KT, right? Now, if I put half-life, we know at time t is equal to T half, AT is equal to A0 by 2, right? This is something which we know now. Now put this condition into this equation. So instead of AT, I'll be writing A0 by 2 is equal to A0, I'm writing as such, minus K. Instead of T, I'll be writing T half. When you solve this equation, you get the value of T half is equal to A0 divided by 2K, right? This is the half-life of the reaction. Which order reaction I'm talking about right here? This is the half-life of the zero order reaction. Okay, as you can see right here, half-life of the zero order reaction depends on the initial concentration of reactant. So if I'll try to plot a curve between half-life versus the concentration of reactant, if I'll try to plot a curve between the half-life versus initial concentration of reactant for a zero order reaction, it's going to be a straight line passing through origin, yes, and its slope is simply going to be 1 by 2K. Yeah, its slope is going to be 1 divided by 2K. Because this equation, it resembles with y is equal to mx, like you can see over here, T half is equal to 1 divided by 2K multiplied by A0. Since A0 I'm plotting along x-axis, T half I'm plotting along y-axis, so it becomes y is equal to this whole term I'll be calling as m, and this becomes x. Y is equal to mx, where m is the slope of the curve, which is going to be 1 divided by 2K, right? I'm sure it's again clear to you, okay? Now people, there is something called as completion time of the zero order reaction. Now what is the completion time of the zero order reaction all about? The time taken for the reaction to complete its 100%, okay? The time taken for the reaction to complete its 100% is called as completion time. Let me write its definition first. The time taken for the reaction to complete 100% of it is what we call as completion time. Yeah? And how do we exactly explain it? Understand. Let's assume I have got the zero order reaction as A gives B, whose rate constant is K. Yeah? I'm assuming the reaction is of the order 0. It is a zero order reaction, correct? Now, for example, at time t is equal to 0, the concentration of reactant is A0, the concentration of product will be 0, correct? Now, when the reaction will start, the concentration of reactant will keep on decreasing with time, and there will be a time when the concentration of reactant will be equal to 0. That means entire reactant has got converted into product, and that time at which the entire reactant gets converted into the product, that time is what we call as completion time. The time taken for the concentration of reactant to reduce from A0 to 0 is what we call as completion time. So at the completion time, what is the concentration of reactant left? The concentration of reactant left, which is denoted by AT, is equal to 0 at the completion time, correct? Now what about my integrated rate equation for the zero order reaction? AT is equal to A0 minus KT, correct? Now we know at time t is equal to T 100%, that means at completion time, what is the concentration of reactant left? It is going to be 0, right? Now put this condition into the given equation. AT value at completion time is 0 is equal. It's going to be A0 minus K multiplied by, instead of T, I'll be writing T 100%, okay? So from this equation, you get something as T 100% is equal to A0 divided by K. So time taken to complete 100% of a zero order reaction, right? Time taken to complete 100% of a zero order reaction is simply going to be A naught divided by K. Yeah? Okay? Time taken to complete 100% of a zero order reaction is simply going to be A naught divided by K, right? So few minutes back, we saw one more thing. Time taken to complete 50% of the reaction, or you call it as the half-life, is equal to A naught divided by 2K, right? If I simply divide these two equations, what I'll be getting? On dividing these two equations, I'll be getting something like this. Time taken to complete 100% of the zero order reaction is equal to 2 multiplied by time taken to complete 50% of the reaction. This statement is only valid for a zero order reaction. Or you can write this thing in the form of a statement. You can say a zero order reaction. Is completed. A zero order reaction is completed in 2 half-lives. Right? You can note it down in the form of a statement as well. A zero order reaction is completed in 2 half-lives. As simple as that, right? Time taken to complete 100% of the reaction is A naught by K. Time taken to complete 50% of the zero order reaction is A naught by 2K. If I divide the two equations, I'll be getting something like this. Time taken to complete 100% of the reaction is equal to 2 times the time taken to complete 50% of it, right? Or you can say a zero order reaction is 100% completed in 2 half-lives, yeah? Okay, you can let me know in the chat box if it is clear to everyone so that I can start with the questions directly. Just let me know in the chat box if everything is clear till here. Just let me know in the chat box fast if everything is clear till here. Yeah? Just let me know in the chat box fast. Right? Perfect. Naman, that is valid for the first order reaction. Yes. What you are saying, time taken to complete 99.9% of the reaction is equal to 10 times T half. That's valid for the first order reaction. That I'll be telling you in the upcoming sessions, not for the zero order reactions. Okay? Yeah? Perfecto. Okay, one more thing about this zero order reaction. That is the units of rate constant. The units of rate constant for a zero order reaction. Yeah? Units of rate constant for a zero order reaction. Well, people, this is the reaction which I have. A balanced chemical equation. I'm assuming it is a zero order reaction. Its rate constant is, for example, equal to K. K is the rate constant of this zero order reaction, yeah? K is its rate constant. So first of all, I'll be writing its rate law. It's going to be equal to K, right? Or let's not talk about the zero order reactions in particular. People, if you remember, I have told you one thing. Rate constant for nth order reactions. This is something which I have told you. Rate constant for the nth order reactions. Its units are, if you remember, it has got two types of units. One is moles later inverse raised power 1 minus n, where n stands for the order of the reaction, second inverse. And it has got one more unit, which is ATM raised power 1 minus n, second inverse. This is something which I told in the last session. Yeah? Now people understand. Since right now we have got a zero order reaction, if we'll be having the zero order reaction, that actually means the value of n is 0. And if the value of n is 0, the unit of rate constant is either going to be moles liter inverse second inverse, or you can write it in terms of ATM. It's going to be equal to ATM second inverse, or if the pressure is in bars, you can write it as bar second inverse or torr second inverse and so on. Yeah? Okay? This is the general unit of the rate constant, correct? You just need to put the value of n. If you are talking about the zero order reaction, put the value of n as 0. If you are talking about the first order reaction, put the value of n as 1. That's it. Ayush, this is the English channel. I'm not supposed to talk in Hindi, bro. Okay? The name of the channel is Vedantu JEE English. Well, there's a Hindi channel of Vedantu as well. You can check that out. You will be definitely getting benefit from that channel as well. Well, this channel is particularly for the ones who cannot understand Hindi. Yeah? Okay? Kethavat, maybe after this chapter, I'll be starting the solutions? Okay, just let me know in the chat box if it is clear to everyone. Give me some green signal from the chat box so that I'll move on. Yeah? Give me some green signal from the chat box so that I'll move on. Clear to everyone? Okay, so let's try to solve few questions now. Okay, these are the curves which I have already drawn. These are the things which I have already told you about the zero order reactions till now. So the first curve valid for the zero order reaction is going to be rate versus concentration of reactant. It will be a straight line parallel to the concentration of reactant axis. The second is going to be straight line with a negative slope, and this T half versus A naught, it's going to be a straight line and its slope is going to be 1 divided by 2k, right? We have discussed this in detail. Yeah, and time taken to complete 100% of the zero order reaction is equal to A naught by K. Time taken to complete 100% of the reaction is equal to 2 times the half-life. Time taken to complete 50% of the reaction is A naught divided by 2k, right? And I told you a few minutes back, a zero order reaction gets completed in 2 half-lives as well, okay? These are the things which we have covered till now, yeah? Well, it's the first question which is on your screen. Let's try to solve this question. Let's try to see, let's check it out how these sort of questions are to be solved, correct? Well, Ayush, most important topic from chemical kinetics as per your JEE is concerned, that is going to be your first order reactions and Arrhenius equation. These are the two most important frequently asked questions from your JEE point of view, okay? Even this zero order reaction is sometimes also asked, but many a times frequently first order and your Arrhenius equation questions have been particularly asked from this part, okay? Now, people, let's try to solve this question. Again, it's a very, very simple question. You can try it out. See, I'm given a zero order reaction A gives B. This is the zero order reaction which is given to me. A gives B. It was observed that at the end of an hour, 75% of A has reacted. So first of all, let's assume at time t is equal to 0, the concentration of reactant is A naught, the concentration of product is 0. Correct? This is something which I'll be assuming in every question. Now, it's mentioned in the question. It was observed that at the end of an hour, 75% of A has reacted. At the end of an hour, 75% of reactant has reacted. If 75% of reactant has reacted, that means 25% of reactant is still left in the container, which I'm representing by 80. 80 is the concentration of reactant left after 1 hour, which is 25% of its initial concentration. Since it's mentioned in the question, after 1 hour, 75% of A has reacted. 75% of A has reacted. What does it mean? It means 75% of the reactant has got converted into product after 1 hour, right? Or you can say 25% of the reactant will be still left as such after 1 hour, right? 25% of A naught, which means 25 divided by 100 multiplied by A naught, which comes out to be A naught by 4. So AT value at 1 hour is equal to A naught divided by 4. This is the first condition which is given to me. This is the condition number 1 which is given to me, right? At what time A will be 10% unreacted? At what time T A will be 10% unreacted? So I need to check at what time 10% of reactant, 10% of A naught will be left in the container. I need to check at what time 10% of the reactant will be still left in the container. At what time 10% of the reactant will be still left as such in the container. Well, this is the second condition. You can say 10% of A naught means 10 divided by 100 multiplied by A naught, which means A naught divided by 10. This is the second condition. What am I supposed to calculate? I need to get the value of T. Now, people, I'll be using first of all this condition. By using this condition, I'll be getting the rate constant. See how? What about my integrated rate equation for the zero order reaction? It's AT is equal to A naught minus KT, right? If I talk about the first condition, as per your first condition is concerned, the value of AT is A naught by 4. The value of AT is A naught by 4 is equal to A naught minus K multiplied by T. T right here in the first condition is 1 hour. Okay, it's 1 hour. So from this equation, can I get the value of K? K is going to be 3 divided by 4 multiplied by A naught. When you get the value of K from here, you'll be get it exactly as 3 divided by 4 A naught, correct? Now, people, again, in this integrated rate equation, I'll be using the condition number 2. As per condition number 2, AT is equal to A naught divided by 10 is equal to A naught minus times K. K value we have got to know as 3 divided by 4 A naught multiplied by T. And this T we are supposed to calculate, right? This T we are supposed to calculate. And when you solve this equation, A naught gets cancelled out and T value will come out to be 1.2 hours. So you can clearly say after 1.2 hours, 10% of the reactant will be still left in the container as such, or you can say after 1.2 hours, 90% of the reactant would have got converted into the products, right? Just let me know in the chat box if it is clear to everyone. Just let me know in the chat box if it is clear to everyone, yeah? I want every one of you to say it. Thank you, Zubair. Just let me know in the chat box fast. Yes, Ayush, you can solve this question without these equations as well. It's a very simple question. But the other method, the alternative method of this question, that is something which I'll be telling you. First, I'll finish the zero order reaction. Then I'll finish the first order reaction. Then I'll show you how to identify exactly which one is zero order, which one is first order reaction. Okay. And after that, I'll tell you some tricks by means of which you can solve these sort of questions. Those are simple basic mathematics tricks, your arithmetic progression, geometric progression tricks. Yeah, that's something which I'll be teaching you once first order reaction will be done. Okay. Mohit, I'm doing wonderful. How are you? All right. Oh, it's Vabo's birthday tomorrow. Happy birthday, Vabo, in advance. Perfect, guys. Let's move on. This is a very, very simple question again which is given to me, right? This is a very, very simple question again that is given to me, right? Now the point is how to solve this question. A zero order reaction is 20% complete in 10 minutes. So people, in this question, the reaction that's given to me is A gives B. This is the reaction which I've forgotten to mention over here. This is the reaction which is given to me. Yeah? Understand. The reaction which is given to me, A gives B, right? It is a zero order reaction first of all as per the equation. Its rate constant is equal to K. At time T is equal to 0, the concentration of reactant is A naught. The concentration of product is 0, right? This is something which we assume for every equation. At time T is equal to 0, the concentration of reactant is A naught. Well, it's mentioned a zero order reaction is 20% completed in 10 minutes, right? A zero order reaction is 20% completed in 10 minutes. What does that mean? That means after 10 minutes, 20% of reactant has got converted into the products. If 20% of the reactant has got converted into the product, there will be still 80% of reactant. 80% of A naught will be still left in the container, and the concentration of reactant left after time T is equal to 10 minutes. That's something which I represent by AT. Okay. So a zero order reaction is 20% completed in 10 minutes. That means after time T is equal to 10 minutes, 80% of A naught will be still left in the container. Or you can clearly write it as 80 divided by 100 multiplied by A naught, which comes out to be 0.8 A naught, right? This is my first condition. Now, at what time it will be 80% completed? At what time reaction will be 80% completed, right? So at what time reaction will be 80% completed? Now, let's assume at time T, the reaction is 80% completed. That means 80% of the reactant has got converted into the product, which means 20% of the reactant is still left in the container, and the concentration of reactant left in the container is something which I denote by AT. Correct? So at time T, the value of AT is simply equal to 0.2 A naught. This is my second condition. Right? Now people, what about the integrated rate equation? Integrated rate equation for zero order, AT is equal to A naught minus KT, right? If I use the first equation, if I use the first condition, in the first condition, what is the value of AT? It is 0.8 A naught is equal to A naught minus K multiplied by T. T is 10 minutes. Right? Okay. So from this equation, you can get the value of K over here. K will be simply 0.2 A naught divided by 10. This is the value of rate constant. Which I got, right? Now people, in the same integrated rate equation, I'll be using the condition number second. Well, as per the condition number second, AT is equal to 0.2 A naught 0.2 A naught is equal to A naught minus K value you have got to know as 0.2 A naught divided by 10 multiplied by T. This A naught gets cancelled out. So by solving this equation, T value will come out to be 40 minutes, right? So after 40 minutes, you'll exactly see 80% of reactant would have got converted into the product, or you can say 20% of the reactant will be still left in the container, yeah? Exactly, first find K, then find T, that's it. Use the first condition to find the rate constant, use the second condition and get the value of T, which we are supposed to calculate, yeah? Zubair, that's enough. That is enough. That is enough. If you are solving the Balaji publication book for physical chemistry, that's enough. Perfect. So people, let's move on. Okay, this is one more question that's given to me, right? See, look at the question carefully. We are given with a table, a very, very simple and ordinary question this is. For a zero order reaction, calculate the rate constant. The reaction that's given to me is A gives B. This is the reaction which is given to me, a balanced chemical equation. Okay, a balanced chemical equation. Now people, first of all, there is a table given to me. At time t is equal to 0, the concentration of reactant is 1 molar. So at time t is equal to 0, the concentration of reactant is 1 molar. That means the value of A naught, initial concentration of reactant, is 1 molar, correct? At time t is equal to 120 seconds, the concentration of reactant is 0 molar. And the time taken for the concentration of reactant to reduce to 0 molar, that time is what we call as completion time, right? That time is what we call as completion time. So completion time of the zero order reaction is also given to me. It's given to me as 120 seconds. This is something which is given to me. What do I need to calculate? I need to calculate the rate constant. A very, very simple and ordinary equation, right? Time taken to complete 100% of the zero order reaction, that is A naught divided by K, and A naught divided by K is 120. So from here, you get the value of K. K will be equal to A naught divided by 120. A naught value, initial concentration of reactant, that's 1 molar divided by 120. And what are the units of rate constant of a zero order reaction? That's simply going to be moles, liter inverse, second inverse, right? A very, very simple and ordinary question this was, yeah? Okay. This is the answer of the question. Hello Vipin, how are you? Perfect. Just give me some green signal again from the chat box so that I'll get to know that you guys got it. Just let me know fast. Yes? Perfecto, guys. Wonderful. So, this is the question which is going to be your homework. You're going to give it a try and you'll be letting me know the answer of this question in the chat box. Oh my God, I showed you the solution as well. I'm really sorry. Aniket, completion time is equal to A naught by K. It's not A naught by 2K. A naught by 2K is half-life of the zero order. Okay, we have got one more question over here. See people, what is the difference over here? We have got one more question. Understand this question properly. Understand this question properly. A very simple, but you can make a mistake in solving this question. See, first of all, I'm given with a zero order reaction as a balanced zero order reaction is given to me as 2A gives products, right? Since whatever questions we have solved till now, everywhere the stoichiometric coefficients of reactants used to be 1. But right here in this question, the stoichiometric coefficient of the reactant is 2. Okay. In the last session, if you remember, I told you rate constant of disappearance of reactant is equal to rate constant of the reaction multiplied by stoichiometric coefficient of that reactant. Okay. Okay, this is something which I've told you in the last session, if you remember. Correct? Now we will understand. Well, as per the given conditions are given, as per the given conditions, half-life of the reaction is 120 seconds. Half-life of the reaction is 120 seconds, right? Let's assume the rate constant of the reaction is represented by K reaction. What about the formula for half-life of a zero order reaction? It used to be A naught divided by 2K. But remember, whenever stoichiometric coefficient will be involved in the reaction on the reactant side, at that time, you won't be directly writing the rate constant of the reaction, you'll be writing the rate constant of disappearance of A. This is basically equal to 120 seconds. This is basically equal to 120 seconds, right? And the initial concentration is given in the equation, that's equal to 2 molar, right? So 2 gets cancelled. So Ka value from here, you'll be getting as 1 divided by 120 moles liter inverse second inverse. What is this Ka? Ka is the rate constant of disappearance of A. But what am I supposed to calculate? I'm supposed to calculate the rate constant of the reaction. And people, we know rate constant of disappearance of A is equal to rate constant of the reaction multiplied by stoichiometric coefficient of A. So you can clearly say rate constant of reaction is equal to Ka divided by stoichiometric coefficient of A, and the stoichiometric coefficient of A is 2. So Ka value you got as 1 divided by 120 multiplied by 2. The value you'll be getting as it's 1 divided by 240, and its units are simply moles liter inverse second inverse. This is the rate constant of the reaction which I was supposed to calculate, right? So you'll be getting one option given as 120 as well, but do not mark this option. This is the rate constant of disappearance of A, because in the reaction, on the reactant side, you are given with the stoichiometric coefficient over here, correct? Whenever on the reactant side, you'll be given with the stoichiometric coefficient. At that time, in this expression, you won't be using a rate constant of the reaction over here. You'll be using the rate constant of disappearance of A. Yeah, and once you get the rate constant of disappearance of A, you can clearly get the rate constant of the reaction as well. Okay, and people, these are some examples of the zero order reactions. These are something which you are going to remember directly. Okay, the first reaction is photochemical reaction between H2 and Cl2. Whenever H2 and Cl2 reacts in presence of H nu sunlight, it leads to the formation of HCl. This is one of the example of the zero order reaction. Similarly, decomposition of Hi over gold. It is one more example of the zero order reaction. And at the same time, decomposition of what? NH3 over molybdenum, right? That's again the example of the zero order reaction. You need to remember these three reactions. There are few more, 2-3 more reactions given in your NCERT. So do remember those reactions as well. Yeah? Yes, Akash, you can do that. You can do that. Perfect. Do remember these reactions, okay? With this, your zero order reactions are over, okay? In the next session of the chemical kinetics, we'll be starting with the first order reaction, which is the most important topic from the chapter, right? The ones who have not joined into the pro subscription yet, guys, do get enrolled in the pro subscription as soon as possible, because the next batch is starting on 21st of June. It's not 14th of June, it's 21st of June, right? 21st of June, next batch on the actual Vedantu platform is starting. So do get enrolled. This is the course fee for 1 year classroom program. Yeah. But if you are new to Vedantu, you have no idea about how the actual Vedantu classrooms look like, you can take the subscription for a month, right? You can take any one of these plans. And while enrolling, there is a link in the description box of the video. You need to click on the link. Use the coupon code as WSPRO if you want me to train you personally, right? So do use this coupon code. Do use this coupon code while getting enrolled if you want me to train you personally, yeah? Okay, the next batch is starting on 21st of June on the actual Vedantu platform. Okay, there is one more link in the description box, that's for the Telegram. Do click on the link, get added to the Telegram group and stay updated about the classes. And the ones who have not liked the video yet, please do like the video, share the video with your friends, and do not forget to subscribe to the channel as well. Well, people, it was nice meeting you. I'll see you guys tomorrow at the same time. Okay, till then, you take care. Bye-bye. God bless you all and love you all. Take care, guys. See you tomorrow. Bye-bye. Good night.